In this session, we are going to discuss in detail the motion of a stationary charge in transverse electric and magnetic fields. This topic is a part of our syllabus for the 4th semester B.Sc Physics core paper Electrodynamics 1. In the last session, we had dealt with the explanation of how a stationary charge when placed in a transverse electric and magnetic field, that is a stationary charge when placed in mutually perpendicular electric and magnetic field executed the cycloidal motion. I think I will very briefly repeat the motion of the charge particle in crossed electric and magnetic field. That is, initially I am placing my charge particle at rest at the origin. When the particle is at rest, its velocity is 0, no magnetic force acts on it because Fb is equal to Qv cross B. The charge particle is only under the influence of the electric field and hence an electric force Fe given by Qe. This electric force accelerates the charge particle along the direction of the electric field, and as the charge particle gains velocity, a magnetic force acts on it which will curve the path of motion of the charge particle. Because of the electric force, the velocity of the charge particle will increase. As velocity increases, magnetic force will increase and the particle it will trace out a more curved path, and by the time it turns towards the y-axis, it moves like this and turns towards the y-axis, it is now beginning to move against the direction of the electric force. That is, as the charge particle moves down, it is moving against the electric force, means the velocity of the charge particle will reduce. As velocity decreases, the magnetic force will also decrease, and by the time it touches the y-axis, its velocity will be 0, magnetic force is 0 and the particle is completely at rest. And this process or cycle continues and the charge particle executes a cycloidal motion. Now what we are going to do is the mathematical proof of the cycloidal motion. The only information at hand for us is that the electric field is acting along the z-axis, magnetic field is acting along the x-axis, that means B is equal to Bi cap, E is equal to E k cap, and the particle is tracing out some kind of motion in a plane perpendicular to that of the magnetic field. That means the position vector of the particle is, it has only coordinates along the y and z directions, that is r equal to yj cap plus zk cap. This is the only information there at hand for me, and also the initial conditions. What is meant by initial condition? At what is the state of the particle at t equal to 0? That is the initial conditions of the particle. So, initial condition means at t equal to 0, what is the position of the particle? That is, its x, y and z coordinates are 0, x equal to y equal to z equal to 0 because the particle is at the origin. And what is it is at? It is in a state of rest. That means its velocity components Vx, Vy, Vz also equal to 0. So, this is the information at hand with me when I start my derivation, and I have to prove that this charge particle is going to follow a cycloidal path. So, what is the root in this derivation? What is the mathematical process or mathematical steps that I am going to follow here? First, I am going to find out the Lorentz force acting on this particle. The particle is placed in a combined electric and magnetic field. So, I am going to find out the net Lorentz force acting on the particle, and as you all know, any force must satisfy Newton's second law of motion given by F is equal to ma, and I am going to equate my Lorentz force to ma, and from that equation I am going to reach the components of velocity of this charge particle, this moving charge, that is I am going to find out Vx, Vy and Vz. From that, by integrating Vx with respect to time, that is integral Vx dt gives me the x coordinate, integral Vy dt gives me the y coordinate, integral Vz dt gives me the z coordinate. Thus, I get the x, y and z coordinate of my charged particle. Once I get the coordinates of the particle, I can know how each of these coordinates vary with time and I can trace out the path followed by the charged particle. So, this is the route that I am going to follow in this derivation. So, firstly, after writing these, I have written down whatever things are given, that is a magnetic field along BI, E is equal to EK, R equal to Yj plus Zk. From R I can write the velocity vector also. Since there is motion only along the y and z axis, I will write it as Vyj cap and Vz k cap. And acceleration is equal to, as you know, it will be Ayj cap and Az k cap. That I write in terms of velocity as dvy by dt j cap plus dvz by dt k cap. Now, I am going to write down the total Lorentz force acting on the charged particle, that is equal to F. F is equal to a force due to the electric field and a force due to the magnetic field. Okay. So, I am going to replace this with E k cap plus Q into, I have to find out V cross B. How do we find out V cross B? I find the determinant of V and B. Determinant of V and B means Ijk, the components of V. X component is 0, Vy, Vz, and B has only one component along the x axis. So, B 0 0. So, this is equal to, I get it as J cap B Vz minus K cap B Vy. So, I am going to substitute these terms here. So, I will get it as, this is equal to Q E K cap plus Q into Vz B J cap minus Q into Vy B K cap. I am going to group the K component terms together and write the J component terms separately. So, that I get Q Vz B J cap plus Q E minus Q Vy B K cap. This is my equation 1. So, I have wrote down the Lorentz force corresponding to this charged particle. Now, what I am going to do? As you know, any force must obey Newton's second law of motion, that is F is equal to ma. So, I am going to equate this equation to Newton's second law, the expression for force as per Newton's second law, that is F is equal to ma, that is equal to m into, in the place of a, I am going to give this one, dy by dt j cap plus dvz by dt k cap, m into dvy by dt j cap plus dvz by dt k cap. Now, I think we can equate both these equations. Let this be equation 2. On equating 1 and 2, I get Q Vz B. Both these forces can be taken as equal. So, what I do is I equate the J components together and I equate the K components together. So, that I get m into dvy by dt is equal to the J component here Q Vz B and m into dvz by dt is equal to the K component here, that is Q E minus Q Vy B. Now, from these two equations I can find out what is dvy by dt. I divide on both sides by m of both these equations. So, I get dvy by dt is equal to Q Vz B by m and dvz by dt is equal to Q E by m minus Q Vy B by m. So, I have got two first order differential equations in terms of But the problem with these equations is that both the equations involve both the variables. That is, the first equation involves Vy and Vz, the second equation also involves Vy and Vz. So what we have to do is, we have to write an equation, let it be first order or second order, but in terms of only one variable. So what I am going to do is, I am going to write the second equation that I have got in terms of Vy. Vy equal to, in that manner I am going to write. Before that, I have to do one simple substitution also. I am going to replace Qb by m with omega. I am going to replace Qb by m with omega. Is it correct? So in the last session we had learned the radius of the circular path in cyclotron motion is equal to r equal to mv by qb. From this I isolate what is qb by m. So qb by m is equal to, you get v by r, linear velocity by radius, that is the angular velocity omega. So I can very easily substitute all qb by m with omega. So the first equation becomes dvy by dt is equal to omega vz, and the second equation becomes dvz by dt is equal to, the first term does not have a qb by m factor, but I introduce one by multiplying the numerator and denominator by b. So it does not make any change, and I isolate out qb by m, so that I can write it as omega e by b minus omega vy. From this equation I am going to write down what is vy. This I give as equation 3, and I am going to write down vy from this. For that I first have to divide throughout by omega and then rearrange, so that I get vy is equal to e by b minus 1 by omega dvz by dt. Let this be my equation 4. Now what I am going to do is, I am going to substitute this 4 in 3 so that my vy gets eliminated from here. Vy has e by b, a constant, minus 1 by omega dvz by dt, that is, I will introduce the variable vz here, so that both sides of my equation has only one variable, which is vz. So I am going to substitute 4 in 3. So that I get, when you substitute it here, d by dt of e by b is a constant, the derivative of a constant is equal to 0. So that term vanishes, minus d by dt of minus 1 by omega dvz by dt. So that becomes 1 by omega d square vz by dt square is equal to omega into vz. Or I can write that equation as d square vz by dt square is equal to minus omega square vz. What is this? This is a very famous second order differential equation which represents a simple harmonic motion. And the advantage of this equation is that it has a standard solution. So the solution of this equation is given by Vz is equal to, all of you know it, Vz is equal to a sine omega t plus phi. This is the form of the solution. But here a and phi are unknown quantities, still we have got what is the form of the solution for Vz. Now I give this as equation phi, and from the Vz that I have got, I am going to write down what is Vy. I am going to substitute equation 5 in equation 4. So substituting 5 in 4, I get my Vy is equal to, first term is a constant e by b minus 1 by omega. I have to find the derivative of Vz with respect to time. D by dt of a sine omega t plus phi, what is it? It is a omega cos omega t plus phi. Omega cancels, I get my Vy is equal to e by b minus a cos omega t plus phi. Okay, so let this be my equation 6. So I have got the equation for Vz, I have got the equation for Vy. The only unknowns here are a and phi. Now we have to determine A and phi, then only our solutions for Vz and Vy becomes complete. Now how do you determine A and phi? So that is our next step, to find A and phi. To find A and phi, any unknowns in this procedure, what we are going to do is, we are going to apply the initial conditions. That is, at t equal to 0, Vx equal to, Vy equal to, Vz equal to 0. So this is the initial condition that I am going to apply in my equations here. That is, I am going to apply in Vz and Vy. Okay. So first I will apply it to Vz, that is at t equal to 0, the velocity of my particle is 0, particle is at rest. So I get applying the initial conditions, to equation 5. Applying it to equation 5, I get 0 equal to A sin phi, because omega t will vanish, Vz will vanish. 0 equal to A sin phi. What is the meaning of this? The product of two terms equal to 0 means either the first term, either A should be equal to 0 or sin phi must be equal to 0. If A is equal to 0, what will happen is, my Vz will be all the time, at all times my Vz will be equal to 0 if A is equal to 0. That means there will be no velocity of the particle along the z direction, or there will be no displacement for the particle along the z direction. That is not possible, because we know that our particle is showing some kind of displacement along the z axis. So that is not possible. We cannot consider A to be 0. That means who must be 0? It implies that A cannot be 0, but sin phi is equal to 0. Sin phi equal to 0 means my phi is equal to 0, because it is for sin 0 that you get the answer as 0. So I have got one of the unknown things, that is phi is equal to 0. So when we applied the initial conditions to the equation for Vz equal to A sin omega t plus phi, we got phi equal to 0. Now we are going to apply our initial conditions to the equation z, equation 6, that is the equation for Vy. Vy is equal to E by B minus A cos omega t plus phi. So applying the initial condition means I am going to give t equal to 0 and Vy equal to 0. So that I get 0 is equal to E by B minus A cos, my t is 0 and I have got phi to be 0 just now. So that this whole thing becomes 0. What is cos 0? Cos 0 is 1. So I get into 1, or A is equal to E by B. Now we have determined both the unknowns in Vz and Vy. So that I get Vz is equal to E by B sin omega t, and Vy is equal to E by B minus E by B cos omega t. I have derived the equations for Vz and Vy. So we have reached the second step of our derivation. First we wrote the Lorentz force. From the Lorentz force we have gone through a number of mathematical steps, a series of mathematical steps, and we have got Vz and Vy. Now what is Vx? Vx is always equal to 0, because the particle has no motion along the direction of the electric field, or the particle has no motion along the direction of the magnetic field or the x-axis. So Vx is eternally 0. So I have got Vz, Vy and Vx. Now what we are going to do is the final stage, that is to find the x, y and z coordinates of the charged particle. I am going to find out the x, y and z coordinates of my charged particle. Okay. So to get the x coordinate, what do I do? What do you do to get the equation for a coordinate? So we know the equation V is equal to dx by dt, or x is equal to, how do I get it? Vx into dt, or it is equal to integral Vx dt. So since Vx is equal to 0, x is equal to 0. So x is always equal to 0 in this case. Next what I do is I find out y. How do I find out y? I integrate this equation with respect to time. So I will integrate Vy with respect to time, that is equal to integral E by B minus E by B cos omega t dt. That is equal to, I will get the solution, E by B, integral E by B dt is equal to E by B into t minus E by B cos omega t. How do I integrate cos omega t? Integral cos omega t dt is equal to sin omega t by omega. So that I get the solution as E by B omega sin omega t plus a constant of integration. Whenever you integrate a quantity, you must give a constant of integration there. This constant of integration again becomes an unknown in our situation. So what do you do? To eliminate an unknown, again we use the initial conditions, that is at t equal to 0. Here I am going to give at t equal to 0, x equal to y equal to z equal to 0, because the particle is placed at the origin. I am going to apply that condition here. So when y is equal to 0, E by B into t, t is 0, E by B omega sin omega t, sin 0, that is again a 0, so that I get my C to be equal to 0. So what is the equation for my y? My y is equal to, I get the y coordinate as E by B into t minus E by B omega sin omega t. So I have determined x and the y coordinate. Next, finally we have to find out the z coordinate from the z component of velocity. So z is equal to integral Vz dt, that is equal to integral Vz is E by B sin omega t dt, that is equal to E by B. Integral of sin omega t is minus of cos omega t by omega plus c. So what did I get? Again a constant of integration which has to be eliminated, again using the initial condition. Initial condition means I give at t equal to 0, z equal to 0. So applying initial conditions, what do I get? I get 0 equal to E by B into E by B omega I take out minus cos omega t, or I get it as minus cos 0 is 1 into 1 plus c, or my c is equal to E by B omega. So I substitute it here, so that I get the complete equation or the precise equation for z. Z is equal to E by B omega minus E by B omega cos omega t. Now I have got all the three equations for the three different coordinates, that is I have got x equal to 0, y equal to, what I am going to do is a slight variation here. I am going to take E by B omega common factor out. So y is equal to E by B omega into, then I have to multiply with omega t minus sin omega t, and z I got it as E by B omega into 1 minus cos omega t. These are the three equations that I got for the three coordinates. Here again, for simplicity, I make one more substitution, that is I am going to substitute E by B omega with r. Is it possible? E by B omega is equal to, E by B means linear velocity by angular velocity is equal to the radial distance r. So I am going to substitute these with r, so I get my y is equal to r into omega t minus sin omega t, and z is equal to r into 1 minus cos omega t. So I have got the equation for x, I got the equation for y, and I have got the equation for z. But I do not think on seeing this you can say what is the path traced out by the particle. You cannot very easily say from these three equations for the coordinates of the charged particle what is the equation traced by it. So I do a bit of rearrangement and a little bit of mathematical steps more. What I do is I take the equation for y. Y is equal to r into 1 minus cos omega t. I write this equation in terms of y is equal to r into, it is not 1 minus cos omega t, it is omega t minus sin omega t. So what I do is I take all the terms to this side except r sin omega t, that is I write y minus r omega t is equal to minus r sin omega t. I write it as y minus r is equal to minus r sin omega t. Next I rearrange the equation for z, that is z is equal to, we had got it as r into 1 minus sin omega t, that is equal to z minus r. I am writing it in terms of z minus r is equal to minus r sin omega t. I think here it was cos omega t. Z is equal to 1 minus r into 1 minus cos omega t. So, I write this as z minus r is equal to minus r cos omega t. What do? I square these two equations. On either sides I square them and I add them, so that I get the final answer as y minus r omega t the whole square is plus z minus r the whole square is equal to r square. This is the final answer that we get. What I did was I squared these equations and I added them, so that I got y minus r omega t the whole square plus z minus r the whole square is equal to r square. Now, what does this equation indicate? You must be familiar with the form x minus a the whole square plus y minus b the whole square is equal to r square. That represents the equation of a circle lying in the xy plane, having centers at small a and small b and radius r. Similarly, this equation is also the equation of a circle having its center at 0, x coordinate is 0, y coordinate is r omega t, z coordinate is r, having radius r, and it is lying in the yz plane. Now, what does that mean? We have got the equation of a circle. That means our x, y and z coordinates, that is our charge particle, is a point on the circle, and this circle is moving forward along the y axis. See the speciality of the sender. The y coordinate of the sender varies with time, r omega t. It varies with time with a velocity r omega, that is the y coordinate of my circle, the center of the y coordinate. The y coordinate of the center of my circle is moving forward with time, so that my charge particle is lying on a circle on the rim. You can imagine it to be lying on a rim of a wheel, and as the wheel moves forward, the particle is progressing forward. So, as the wheel moves forward, suppose you have a circle here and my charge particle is a point on it. As the circle moves forward, the point traces out a path like this. You can very easily do it at home. Take a coin, mark a point on it and roll the coin. See how that point moves. It will move exactly in the same fashion as this, or my charge particle follows a cycloidal path. So, only from the limited information that we had at hand, now we have mathematically proved that our charge particle is following a cycloidal path. I hope this session is clear to all of you. If you have any doubts, you can contact me. Till we meet in the next session. Thank you.